Okay, so just wanted to make sure we're clear on some things about tides. So this could be Oceans 2.1 um, tides with some gravity stuff because gravity is kind of important. So there's, right, so we're really talking about Isaac Newton's law of gravity here that he did a long time ago. That's him, handsome fellow, real smart dude. Don't get all mathematically freaked out here, anybody. We'll just mention a few things. So his universal law of gravity, that's it there. That's the equation. We're not going to use it. You're not going to need to know it for anything, but some of you, this might be useful to understanding. So essentially, if we're talking about the gravity between two objects, here's the two objects, mass 1 and mass 2, any two objects, the mass of the two of them, and then the r is the distance between them. So fundamentally, this probably makes sense to you. All we're doing is multiplying their masses together, and you divide by how far apart they are squared. That's the important thing for what we're talking about. So it says here, as the distance between a pair of objects increases, the force of gravity experienced by the pair of objects decreases. That makes sense. If two things are gravitationally pulling on each other and they get farther apart, it'll weaken. The gravity between them will get less. And not only does it just get straight less, it's squared, so it gets a lot less. Okay, so if we looked at this mathematically and we use real simple numbers, and we said the mass of one object was 1, the mass of the other one was 1, and they were 1 unit of distance apart, we're just squaring that. The gravity between them is 1g, and then g is a constant number. We don't even need to worry about it. Just say 1g, right? But if we doubled the distance between them, the gravity doesn't just half, right? It's not just half of what it was. It's now a quarter of what it was because we square that distance between them. Does that make sense? If we had other numbers here and we doubled the mass of this object, right? Oh, let's say this one, just stay over here. We did this and we get 1, then we double this, then we get 2g, right? So if you double 1, then you get twice the gravitational attraction between them. So all we're really talking about today is the distance, because we're talking about how much further away the sun is than the moon, right? So as that large, even though the sun is a lot larger than the moon, it gets so much further away that the gravity weakens a lot. And so the moon turns out to be so much more gravitationally influential because of this. So again, if this doesn't make sense, the equation, don't worry about it. Just know that as it gets farther away, the gravity weakens greatly with distance. So as far as the tides then, let's see if this bad boy plays. I'm getting a new computer here within a few days, so we won't have slowness like this. So here's the sun over here. And so what we notice then, as the moon goes around, the moon is what's in charge of the tides, right? And technically speaking, when we talk about the tides coming in, when you're talking about the ocean, the water coming in as a result of the tides, right? So this is the tidal bulge of the planet. Can we get a replay? Right, so everywhere that's underneath the moon. So if you were here on the Earth as the moon traveled around, that's where the gravitational tide would be. Okay, wherever's right underneath the moon, and directly opposite. Right, we notice there's a bulge on the other side, which we'll talk about here in a second. So everywhere the moon is a high tide, and then on the opposite side of the Earth is a high tide. The 2 points in between, perpendicular, are where the low tides are. So why is there a tidal bulge on Earth on the opposite side? Obviously the moon's gravitational pull on this side is pulling it towards inertia. Then, if you remember from learning inertia a long time ago, is just the tendency for an object to keep going in the direction that it's moving. Okay, just like if you're driving in your car and you make a real sharp turn to the left, your body keeps going in that straight direction. You feel like you bump into the car door with your right shoulder, but really you keep going straight and the car comes at you, right? So what's happening here then is the Earth is being pulled towards the moon. I guess the other part of inertia is then objects stay in place until a force acts on them. So the oceans on this side, the Earth is being pulled towards the moon, and then the oceans tend to stay in place, so it bulges out on that side in that straight line. So we get this gravitational bulge over here, another tidal bulge on the other side due to inertia. So we have wherever the moon is, high tide right below it, and on the opposite side, low tide, low tide. So we can throw the moon phases in here. So this is the same thing. If you feel like reading all of that, this is the factors that influence high and low tides of the moon. So we have a high tide. That's what we just said, when the moon is below or on the opposite side, or because it's below would be the closest. Okay, and then in between is low tides. So just like that, there's the moon. So ignoring the sun for now, wherever the moon is, high tide, low tide, low tide. Right, and then the Earth rotates underneath that. Remember, we talked about moon phases. So the Earth or the moon will be sitting there for 2 or 3 days. So as we rotate around and you hit that spot, high tide, and the moon changes a little each day. So if you look at tide charts, that's why every day they're slightly different. The other one is the sun, and that comes into this spring and neap tide. So what we end up happening is, if the moon, the sun, and the Earth are all in a straight line, then the high tides are magnified. So we have higher high tides. And then when they're perpendicular, we have the lower high tides. Okay. So in this case here, this would be spring tides on both these situations here. So if we have a new moon or a full moon, we'll have spring tides in these locations. So these are the high tides because of the moon, spring tides because of the added additional gravity of the sun. And the same thing over there. So those would be our spring tides, higher than normal high tides. And these are the neap tides. So this is still high tide, right? The moon is what determines high tide. But now, because it's perpendicular with the sun's influence, it's just lower than normal high tides. So we call them the neap tides. Okay? Spring and neap. Ignore that. And so this is just the whole thing showing right there. So if the sun's over here, here's our new moon. We'll have the spring tide here, spring tide over there when it's a full moon. Neap tide, right? Full month for the moon to go around. Okay, so hopefully that was helpful with the spring and the neap tides, just clarifying the little activity that you did there.